Hi everybody, this is Mr. Folly, and welcome to our Real 6.1 again, the atom. So we're going to do the definition of the atom, the parts of the atom, a little bit on the periodic table, metal, non-metal, metalloid, the laws that helped us figure out where the atom were, and then Dalton's great theory. So let's hop right into it. The atom. The definition of an atom is the smallest part of an element that still retains those properties. If I have a big piece of gold and a little piece of gold, they have the same intensive properties. So those things that let you identify it as gold will be the same. But what will be different, of course, would be like the mass or the shape of it. If you keep cutting it down, eventually you will cut it. So if you have an atom of gold, it still has all those properties, yellow, shiny, blah, blah, blah. But if you cut it smaller than that, if it's cutting is probably the wrong word, you split the atom and it's no longer gold. It turns into something else with entirely new properties. And that's true for anything. Parts. If you don't know this, shame on you. Protons. The mass is 1, the charge is positive 1. Protons determine the identity. The number of protons is also often called the atomic number. It's also frequently called Z. I don't know why. Electrons determine your reactivity. They also determine your charge. The mass of an electron is 0. The charge of an electron is -1. Neutrons determine mass and stability. The mass of a neutron is 1. The charge of a neutron is 0. Notice protons and neutrons have mass. All right. Now this part about how can an electron have no mass? How can something have no mass? They do have mass, but it's 10,000 times less than the other two. So it's negligible. What does negligible mean? So small or so insignificant, it doesn't matter. So basically take anything that Sean Lenz says, 40, and you'll understand that it is a negligible comment. There you go to that happy chemistry class. Periodic table. Periodic table. 1, 2, 3, 4, 5, 6. Columns are called families or groups. So columns go up and down. Columns support buildings, so they go up or down. So I use this blue one. Columns go up and down. So this would be column number 1, column number 2. If I were to ignore this, 3, 4, 5, 6, 7, 8. Columns are called families or groups, and the reason why they're called families is they have similar properties. So what has similar properties? Columns have similar properties. Rows are called periods. They do not have similar properties. And we'll get into details later on that when we get into the periodic table unit. So you need to know if I ask for an element that's on the third group and the third period, or third group, let me pick a different one, and the fourth period, that would mean I'd go down 1, 2, 3, 4. So I'm on the fourth row, and the third group would be right here. So the third group would be in the boron column. Get out your periodic tables, hit pause, go get your periodic tables, go on. And then 1, 2, 3, 4 down from that would be gallium. Be sure when you're looking at the periods to count the top one, which only has a hydrogen and a helium in it. Okay. Metals. Where are they in the periodic table? Well, as we saw in our video today, metals are roughly 3/4 of the periodic table. 2, 3, 4, 5. Oh, there we go. So, and there's a little stair step that helps us discern where they are, etc., etc., etc. So it's the stair step that goes from boron is on top of it, silicon, germanium. And if you look at that, seriously, get out your periodic table. Go get your periodic table. You'll be able to see where it is. and I will highlight for you the things with two sides on that. Now there's one little trick. There's aluminum right here which fits the, oops, I'm sorry, there's the little stair step thing. Anything that's on the left of the stair step is a metal. Left of steps are metals. There's one exception to that, and that is hydrogen. If you did not know that hydrogen is not a metal, there's something wrong with you. Seriously. Hydrogen is a gas. Gases aren't metals. Aluminum, metal. Okay. Properties of metals. They are lustrous. Which means they're shiny. If you put down that metals are full of shins, you will lose points. Take away all the points on the whole page. So they're lustrous. They're malleable. That means if you hit it with a hammer, it will bend and change its shape. So if you think of an aluminum can, if you squeeze an aluminum can, it will change shape. You'll be able to bend it. The opposite of malleable would be brittle. So if you took a hammer and hit a drinking glass, it would shatter into a bunch of pieces. Or if you think of an old lady's hip when she falls down, her hip will shatter into a bunch of pieces. It will not bend. So lustrous, malleable, ductile. I talked about this in the video today too. That means you can turn it into wires, which I think is directly related to malleability. So let's just malleable, ductile. They're good conductors. Nonmetals are on the right-hand side of the stair steps. Their properties are the opposite of metal. So they, instead of being shiny, they are dull. Instead of being conductors, they are non-conductors. Instead of being malleable, they are brittle. They're not ductile, etc., etc., etc. Just throw a not in front of all the other ones. Metalloids are the semi-metals. Location on the periodic table. They have two sides on the steps. The exception to this is aluminum. If you didn't know aluminum was a metal, shame on you. Properties of metalloids or semi-metals is they are a combo of metals and nonmetals. So for example, a metalloid could be a malleable, dull element. Okay. It doesn't mean that you're kind of malleable and you're kind of dull. It doesn't mean that. It means you have a blend of them. So you would be quite malleable and quite dull. And now we're going into how did we figure out where atoms came from. This is the worst part. Make sure you know the definitions of these laws that I'm going to go over right here. They get to be kind of confusing. Just make sure you can do the definition that's coming up and see if you can follow this if you can. The law of multiple proportions. In the law of multiple proportions, you're looking at different elements or different compounds that have the same number of elements in them. Okay, the same types of elements in them. So all of these are composed of only N's and only H's. Okay. So I just assumed I had a mole of each. So the mass of one N is 14, one N is 14, 2 is 28. 3 H's is 1, 4 H's is 4, 4 H's is 4. And I just rounded it to 1 to make this a little bit easier. The ratios turn out to be kind of simple: 4 2/3, 3 1/2, and 7. If you arrange one of them, there will always be a simple whole number ratio. Okay? So to me, a simple whole number ratio is either a whole number, a quarter, a third, a half, or multiples of those. I know a quarter is a half is a multiple of a quarter, but you get the idea there. Okay? And 2/3 would be a multiple of 1/3. Okay. So this seems weird. So what this means is that if you kept reducing these down, now of course I used a molar mass, and a mole would be 6.02 E23 particles here. So that means I would have 1 of those and 3 of those for that. But if I kept, what happened was people just did experiments and found out that Anytime you did NH3, you got a ratio of 4 2/3. When you did NH4 positive, you got a ratio of 3.5. When you did N2H4, you got a ratio of 7. And they thought it's weird to have these small fractions, these simple fractions or whole numbers. And the reason why you'd have simple fractions and whole numbers is because if you keep reducing them down and down, there must be an entire unit. And that entire unit, of course, is the atom. We'll do a little more in class with that, so if that doesn't make a ton of sense to you, I've got one more slide to try and torture you with it, but we can do here. This means there's a small consistent unit, which is what I just said. If a tire weighs 1 and a frame weighs 14, oh, Mr. Feller, you're so clever. Oh, look at that. They're unsplittable parts of wheel and frame. The chart would be nearly identical. So if I have a bicycle, oh, a tricycle, oh, and one of the 4 bicycles for the sad people that can't even handle a tricycle, your ratios still come out to be 7, something in thirds, and something in halves. Okay, so looking at that, again, we're assuming the frames would always be the same. Now, we didn't assume this. We did experiments and found out, you know what? We always got these ratios of frames. In real life, bicycle frames don't always weigh the same. Okay, I can have, you know, my little Huffy that weighs, you know, 14 for a frame, and then somebody else could have their monstrous mountain bike, which, of course, those of you who are monstrous mountain bike riders know that monstrous mountain bikes are shockingly light that only weighs 5. That's not an option here. This bike frames always end up with these small units of 14. So this means that every bicycle frame has to be the same. There must be a simple unit for a bicycle frame. That simple unit would be the atom. Boy, what a rotten kind of for an atom. This is all I had. Then we have the law of multiple proportions. Sounds like the same thing. Oh, this is the same thing. This is the definition I told you to know. Ratio of masses will have small whole number ratio. These whole number ratios imply a small indivisible unit. Small indivisible unit is the atom. Ratios of mass have a small whole number ratios. This is what I forgot to put in here. 4 different compound types. Okay, that's the law of multiple proportions. Welcome to it. Now we've got a new law, a law of definite composition. And in this one, in the law of definite composition, I looked at NH3. Each one of these samples is NH3. And I took different masses of them. This mass is 95. This mass is 86. This mass is 1.39 E-5. Then what I did was I used my percent composition and figured out the mass of nitrogen here and the mass of hydrogen. The mass of nitrogen, the mass of hydrogen, the mass of nitrogen, the mass of hydrogen. And as I look at these, all of these came up to be the same ratio. So what this says is NH3 is always going to be NH3. Instead of saying molecule here, I should have written ammonia. So any sample of ammonia always has the same ratio of masses. So if they always have the same ratio, again, if you're thinking about bicycle frames, well, why would you? But if you're thinking about bicycle frames, they always have the same ratio. That means every bicycle frame must be the same. You can't have a cheap Huffy and comparing it to some Canon bicycle frame or whatever it is. Every frame must be the same. Every hydrogen or every wheel must be the same. So if they must be the same, that must mean there's a small unit that's consistent. That small consistent unit would be the atom. You can be kidding me, right? This is all that we have. Yeah. Ratios of mass of any size sample will be the same. This implies small indivisible units. Ratios of mass of any size sample of the same compound will be the same. This again implies small indivisible units, atoms. All right. Those laws were the backbone of the atomic theory. All right, sharpen your pencils. Here's the 5 parts of the atomic theory. John Dalton formed an atomic theory made of 5 parts. All matter is made of indivisible and indestructible atoms. Atoms of an element have identical physical and chemical properties to all other elements of the same type. This means that gold in Indiana is exactly the same as gold in Illinois, which is exactly the same as gold in India, or gold in Alabama, or gold in Brazil. It's all gold and have the same properties. It doesn't matter where it came from. Atoms of different elements have different chemical and physical properties. Yeah, if they were the same, they would be the same atom. Atoms combine in simple whole number ratios to form compounds. So this is compounds, plural, right? So if you're comparing different compounds, what is that? Law of multiple proportions. Atoms stay the same when chemical reactions take place. For example, the carbon in sugar turns into the C in CO2 when you burn sugar. The weird thing about this also means that atoms, and this is kind of creepy, are eternal. That means the atoms that we're made up of right now were around in the year 1000, and they were around in the year 1000 BC, and they were in the year 65 million BC, and they're the same atoms, which is really kind of creepy. Now, here's some sadness on here. Here's the reality. Dalton made this sometime in, I don't know, maybe the 1860s or so. I know it was the 1800s, I'm not quite sure. Somewhere between 1840s and 1860s, I think. But all matter is made of indivisible and indestructible atoms. You're wrong. We've split the atom. Nuclear chemistry does that. Atoms of an element have identical physical and chemical properties to all other elements of the same type. Oh, sad. The exception to that is isotopes, which we'll learn about later. Maybe you remember them from biology, but nobody ever does. Atoms of different elements have different chemical and physical properties. Yay! Something that's perfectly right. Atoms combine in simple whole number. Yep. Atoms stay the same. Yep. Now, this is true for chemical reactions. In this very chapter, we'll learn that it's not true in nuclear reactions. Nuclear. I was going to make fun of it. I might as well. Nuclear reactions. To review. Atoms are made of protons, neutrons, and electrons. Periodic table is arranged in families, columns, and periods, rows. Metals, nonmetals, and metalloids are in certain places with certain traits. You should be able to identify those. You should be able to find the stair-step thing. Atomic theory is based on a few observations, laws. Remember, these laws are based on observations. They kept doing experiments, and they kept looking at the results, and they played around with the math, and the atomic theory has been tweaked over the years, which is why poor Dalton doesn't have things as perfect as he would like them to be. So with that, I will end you with the wonderful words of The Simpsons. If you can tell me, what was the guy's name? It wasn't Mr. Adam. I forgot. But he used to always say, up. They tried to get him to say, up and at them. He would say, up and at them, the bad Arnold Schwarzenegger clone. So I will see you tomorrow when you are up and at them. Good night.